So let's continue fixing this oscilloscope where the synchronization isn't working or the time base triggering. It's basically just free floating, not synchronizing to the signal. It's sort of synchronizing, maybe in the TV mode in some situations, or not even this. In the TV mode it sometimes sort of catches on, but not really properly. And it's normally not supposed to be used in the TV mode anyway. We have to start looking for the problem in the synchronization and time base circuitry, which is on the right side. And this board is the time base, and here's the synchronization circuitry. And now let's turn it off and let's start looking for some better component. Here's the horizontal centering potentiometer, which I already fixed. I fixed a lot of poor contacts in the switches using a contact cleaner. I fixed the high voltage and heater power supply, which had bad capacitors. But I still have to fix this. It contains a lot of transistors and they are socketed, so they're easy to test or replace. I started going through the transistors using a transistor tester and I just put them in, and I already tested the ones with the green dot on them, and this one has 4 pins, so I have to figure out how to put it in. One is probably just the housing. And of course this video might be interesting because the brain fog is still there. I can see 2 pins are actually connected on the board to one spot, so let's just put these 2 pins into the same place, maybe. Of course, staying in the view, maybe, hopefully. It's an N-channel DMOS, 25 picofarads gate capacitance, 4.2 milliamps at 2.9 volts gate to source. And the pin configuration, I guess it's a good transistor. So let's put it back, ideally the way it was originally. I tested this transistor, and of course I was testing this one and I forgot to turn the camera on. I was just talking to myself here, and so let's try this one now. This video is turning into a dumb video of me just sticking transistors into this machine, which currently might be more intelligent than me. It's a bipolar NPN transistor, gain 50, about 700 millivolts base to emitter voltage drop, and it seems like a good transistor, so let's put it back. It seems most of the transistors here are bipolar so far, except the transistor here, the first one. And let's mark this one. And looking at it closer, I can see something very sinister here. These oscilloscopes are infamous for their tunnel diodes, which are very prone to failures. And here's one diode. Let's actually take a closer look at it. I guess this one contains just one tunnel diode. It's the thing in the center with the yellow dot. If it focuses, I think it doesn't. Oh crap! How this is possible? This tunnel diode is actually broken in half. Now of course the question is, how could this happen? Was somebody actually soldering a new one into it and corrected by a heat, or did somebody drop it, or did some other component fail and blow this diode apart? Or did the poor diode just fall apart by age? Well, eventually this happens to everybody, but how this is possible? But of course the diode might have failed because some other component near it failed, so it's still a good idea to test the transistors, maybe also to measure the diodes nearby, the capacitors for shorts. Just testing some random components in vicinity, about 0.6 volts voltage drop for all these diodes near it, and they seem good, nothing wrong here. I could test some ceramic capacitors here, if they are not shorted. I can see something other than 0, so it should be good. Here is some capacitor, again something else than a 0, if I'm not blocking the meter display, of course. Of course transistors can also be tested as 2 diodes. Here is some diode, here is some diode. I'm not going to test the transistors, but they can be tested as 2 diodes, base to emitter and base to collector NPN, or collector to base and emitter to base PNP. Here the voltage drops of the transistor are skewed by some other components in the board, 0.36. If I take it out, it should be reading something more sensible, 0.62 and 0.68, base to emitter and base to collector. Sometimes it's not possible to measure the transistor in the board. I'm just demonstrating this, but I've already tested it in this one. Checking another ceramic capacitor near the tunnel diode for a short. Of course, capacitors can be tested for shorts in the board, but their capacitance can't be typically measured in the board. I don't see anything obviously wrong here. No shorted capacitor. It always shows some voltage drop of something near the capacitor, but it's not that short. Already quite far from the tunnel diode anyway, but checking some diodes here, and everything seems fine. Testing every transistor in the board. Talk about working hard, not smart. I ran into a second FET. So I've tested all the transistors in it, all the diodes and all the ceramic capacitors for shorts. Some of them several times because I keep forgetting which ones I already tested. And most of it seems fine, except one suspicious diode and one suspicious capacitor. And I say suspicious, not bad, because the measurement might be skewed by some other components connected to it through the board. So let's go to the suspicious diode. Measuring it using a diode test shows virtually zero voltage drop, which might mean the diode is shorted, but it actually seems to be connected to this coil. And of course the coil with a low number of turns has a very low DC resistance, and it seems to be connected to the diode. Let's try to measure a resistance instead of a diode voltage drop, and it measures 0.0 ohms. But this is measured at DC. What if I connect my ESR meter to it, which is meant to test capacitors, but it basically measures a resistance just like a resistance meter, other than it uses 100 kHz high frequency instead of DC current for the test. And this one actually says 60 ohms instead of 0 ohms. So the diode is not that short. And I guess this 60 ohm impedance is the impedance of the coil at 100 kHz. A shorted diode would still keep showing 0 ohms or something close to it. Of course, I could also desolder the diode to test it, but I'm too lazy. So I'm demonstrating some other ways of testing a component inside of a circuit board. So now let's try to actually connect a ring tester to the diode, which is in parallel to the coil. And the ring tester is showing 44 rings, which means the coil is good and also the diode parallel to it is not shorted. Okay, so we have proven this diode is good without desoldering it. And there is a ceramic capacitor, this one, which shows 0.0 ohms. That's quite suspicious. It could be again some low resistance winding connected somehow parallel to it, but also the capacitor itself shorted. The capacitor seems to go to a diode. It could be shorted through the diode, but I guess I already tested this diode and it was good. It's this one. The diode is actually good. And then also the capacitor goes to some wire going to some other board. And the other terminal of the capacitor is connected to the chassis and the negative rail, or 0 volt rail actually. It's a 22 nanofarad capacitor. Trying to ring test the capacitor together with some high Q inductor and shows 0 rings. This really looks like a desoldering time. One pin of the capacitor is disconnected and measuring on the capacitor, measuring on the board. The short is still in the board, it's not in the capacitor. Let's try to measure the capacitance of it. 23 nano, within tolerance for a 22 nano capacitor, I guess. But then I started thinking, maybe it's not a short, but a switch. And I was trying to move all the switches and I figured out it's this switch switching between a positive and a negative edge for the trigger or something like this. It's a switch, not a short. This thing is quite complex and confusing. There is a pair of capacitors and one of them is always shorted by the switch for the positive or negative or rising or falling edge or something. So it so far seems like there is no other bad component other than the tunnel diode. Well, I'm still not desperate enough to measure all the resistors in the board, but I've measured the ones in the vicinity of the tunnel diode and these ones are good. And of course the measured resistances of the resistors in the board can be skewed down by the surrounding components but not up. When the resistor measures less, it still can be good, but when it measures significantly more than it says, it's probably bad. And the same applies to the voltage drops of diodes and transistor junctions. If it measures less, it can be skewed by something else in the board, but if it measures more or open in forward, it's probably bad. Now let's take a brief look at the bloody complex schematic of it. Here are the inputs, the AC or DC switches, attenuators, the vertical amplifier, the final stage and the vertical plates. And the horizontal deflection plates also have some power amplifier for them. And here's the time base, the double horizontal centering potentiometer which I fixed, the time base setting switches. I guess this entire thing is the time base selector switch, with one position here for the XY mode. And this basically shows the interconnections between all the boards. Now let's go to the time base board. This one is the vertical amplifier, another part of the vertical amplifier, the final stage here, the synchronization amplifier with all the switches here. Here I guess you have some low pass and a high pass filter going through a series resistor and a parallel capacitor, a low pass filter or a high pass filter going through a series capacitor and a parallel resistor then. And this one enables the automatic mode. This one is the TV mode, which seems to send the signal through some additional circuitry, which amplifies it and gives it some threshold, I guess optimized for the vertical and horizontal synchronization pulses of analog television signal, and some logic circuitry here. I guess when I switch it to the TV mode, this amplifies the signal enough so it somehow makes it past the broken tunnel diode. This is again the polarity switch shorting the capacitors I was measuring. This is an AC or DC coupling switch for the time base or synchronization, which basically just sends the signal through a capacitor in AC only mode. And this is an internal or external switch, which basically for external just sends an external signal into it from this input. And there's some sort of an amplifier here. And here's finally the main time base board with the tunnel diode here. It's some sort of an amplifier. Here's the FET transistor, one of the very few ones here. One is here, one is here, and the rest of it is bipolar. And here's a pair of transistors, and I guess only one of them is used at time. And they have their power going through these 22 nano capacitors, and the supply of one of them is always shorted using the switch. Here's the potentiometer setting the trigger level. And when the signal passes the selected trigger level, either on its way up or on its way down, this circuit probably creates a very short sudden pulse, starting the scan. And the point of the tunnel diode is probably to make this pulse very sudden, to basically make its rising edge very fast. Then it's amplified. Here's the diode in parallel to the coil, which confused me. And then it's somehow further amplified here. And there is of course some parallel circuitry to this tunnel diode, so I guess a strong signal with enough amplitude might have made it through this other circuitry, this pair of resistors and a coil, or maybe through some stray capacitances in the circuit. But I don't see any bad components in vicinity of the tunnel diode, so I guess it's the only problem. And of course tunnel diodes are sort of rare. I might have some old stock, but I guess most of the old stock of tunnel diodes already ran out because these diodes are very unreliable. Most of the world's old stock has probably already been used for replacements. And what else we can see in the schematic? Here's the power supply with the transformer. Here's the mains input. Here's the interference filter with the paper capacitor, which will probably explode. I have to replace it for some filter with a polyester or polypropylene capacitor. Here is a discharging resistor, the switch. The filter is before the switch, so the capacitor in the filter can explode even when it's off by this switch. That's a brilliant idea. That's why you never leave the appliances plugged in. Switching it off by the switch is not enough. It's really better to unplug appliances, especially old ones, before you leave the room, let alone the house or apartment. Here's I guess the 120-220 volt switch, a lot of bridge rectifiers, smoothing capacitors, some regulators. What else is here? The calibrator circuitry. This is the input preamplifier and attenuators. That's the same for the other channel. And that's the high voltage power supply, heater power supply, the source of focus voltages and the brightness amplifier, and the blinking and these things. And that's it. And the schematic says the tunnel diode is a GE134, a germanium tunnel diode. Here's the datasheet, and the package seems to be the same thing. And some specifications here. And this also verifies that a yellow dot is GE134 out of these types. Its peak current is 4 plus minus 0.4 milliamps. The saddle current is less than 0.8 milliamps, less than 20 picofarads. Peak voltage 55 to 65 millivolts. Saddle voltage 350 millivolts. And of course I don't have the exact same tunnel diode, but I might try to find some similar. A tunnel diode has a very weird voltamp characteristic, especially in forward, where the current goes up with the voltage, then down, and then back up. So it basically has a negative resistance region here. They can be used in relaxation oscillators up to microwave frequencies. or to give the trigger circuitry some decisive threshold with hysteresis and a very fast rise time. I guess because the oscilloscope is still running without it, the beam is still scanning horizontally, the diode is not an oscillator here, it's just giving it some sort of threshold. I guess when the input signal goes through a certain threshold, the diode suddenly jumps from this point to this one, or the other way. But anyway, for the purpose of replacing it with a different type, the type has to be similar, and every tunnel diode has some specific points on the voltamp curve. One is the peak, and one is the saddle or valley or whatever you call it. It has a certain voltage and a certain current at this peak, and a certain voltage and a certain current in this valley, which should be as close as possible in the replacement. I'm looking at the datasheets of some Soviet tunnel diodes, and this one seems to have the voltages here. The voltage in the peak is 180 millivolts or 0.18 volts, which is way higher, and these are probably the valley voltages, again significantly higher. And of course this one says gallium arsenide tunnel diodes. I guess this is why they have a higher voltage drop than germanium diodes. Soviet diodes starting with A or 3 are probably gallium arsenide, not germanium, so I can skip these. Again starting 3 or A, gallium arsenide tunnel diodes. And then I'm getting to the diodes starting with G or 1, and these types are germanium. But I guess this one is not even a tunnel diode, it's like a reverse diode, which is a different type of very weird diode, which I guess for very low voltages actually passes more current in reverse than in forward. And then another datasheet. Finally some diodes which are tunnel diodes and germanium at the same time. And some of these types are 4.5 to 5.5 milliamps peak. And the voltages at the peak seem to be all a bit higher than I need. Also the valley voltage here. This actually seems sort of close to the 350 millivolts I need. And of course, to make it more confusing, instead of the valley current, the datasheet says its ratio towards the peak current, or some ranges for the ratios. And of course, this datasheet is for multiple different types of tunnel diodes, and I guess I don't have any of these types anyway. But there is another, which actually seems to be a bit more similar, 4.6 to 5.2 milliamps peak current, or 4.5 to 5.1 milliamps, and the voltages seem like 400 millivolts or 420 millivolts, which is sort of kind of close to 350 millivolts, and the voltage at the peak seems to be 65 millivolts, or it actually says no more than 65 millivolts, and the original says 55 to 65. I guess this is close enough, and this one seems to be the closest one so far. And it again, instead of saying the valley current, says the ratio of it to the peak current. It says no less than this, so the ratio is at least 5, which means if the peak current is about 5 milliamps, the valley current has to be 1 milliamp or less. And the original says 0.8 milliamps or less, but well, close enough. Tunnel diodes are sort of rare, so I can't be too picky. And of course the current is closer to the original for the A-type. Here's the actual curve shown in the datasheet, only the first quadrant or positive quadrant. Looking at another type, this one is about 10 milliamps peak current, more than double of what I need. I need about 4. And this thing's about 1.8 milliamps, way too low. So let's go back to the GI or 1i, 304A, which was definitely the closest. I found 2 pieces of this one. One has bent pins, but it's the same. Weird diodes, gold plated. This is really a super odd component. Can I actually test it as a diode? It shows about 380 millivolts, which is close to the 350 valley voltage. It actually randomly sometimes measures 10 millivolts or 11, and sometimes 380, probably depending whether it triggers or not. And the other direction, it's always about 9 or 10 millivolts. And this does not change in this direction, it's always this. But I guess this behavior actually shows it's working. What about the other one? In this direction again, always about 9 millivolts. And the other one, 10, 10, 410, now 419, and now 400 something, and then again it has a very similar behavior and a slightly higher voltage drop than this one. Of course there were probably some differences between individual pieces in production. Let's cut out the old one and let's solder the new one to the pins of it. I don't want to remove the entire board because of this. And of course these diodes are germanium, so they are very sensitive to heat. Of course the thing is, what I'm going to do if I put it in and it still doesn't work? And then it can be because I destroyed it by heat, or because it's not a suitable replacement, or also because there is some other problem in the oscilloscope as well. I might actually do this. This is the board. These are the pins of the original one, which I cut out and it disintegrated. I might use the springiness of these wires and put the new one over them, and hopefully both pins might make a contact without soldering for the testing, to see if this type works and if the polarity is right, because this is another question mark. What do you think about this? And let's watch the new diode explode. Well, it actually seems working. External, internal, AC or DC, rising or falling. This seems to work. Automatic. Well, why the automatic now doesn't work? This thing works. A low pass or high pass filter. High pass probably doesn't work for a sine wave. If I give it a square wave, it works. Or if I give it a higher frequency, I guess it will also work with a high pass. Low pass, high pass, none of them. Automatic doesn't work, but I might be just using it wrong, but this actually works where it didn't work previously. Of course, I guess the probe is not calibrated properly for this oscilloscope, but anyway, nice. It doesn't look bad, does it? And of course you can set the trigger level here. Rising, falling, AC, DC. In the automatic mode it's weird. Now the new tunnel diode is soldered on the pins of the old one, and it seems to work. I was holding the pins of the diode using my tweezers between the body of the diode and the soldered end of the pin to basically take the heat away. Now it definitely works better than before, but I guess there might be some other problem because it doesn't work in the automatic mode. But because the video is getting bloody long, let's leave it for another episode. And now it's already quite usable. So that's it, and if you've made it that far, please consider supporting this channel on Patreon or using the thanks button, and also subscribing, of course. And big thanks to all of you who already support me. This channel wouldn't be possible without you.